we can get started. Hopefully don't lose my voice. Okay. So, let's see, chapter, what are we on, 2.4? 2.5? Sorry, let me get my book there. Well, maybe I won't need it for a while. Okay, 2.5, continuity. Now, remember the four big ideas in calculus. Limits, continuity, derivatives, and integrals, right? So far, we've been focused on limits. With that big epsilon-delta definition, for every epsilon, there exists a delta such that if x was within delta of c, then f of x is within epsilon of your limit L. Does that definition sound familiar? Our definition for a limit. So we've covered limits, what limits are, that definition captures it exactly. Now, you might be thinking to yourself, well, I don't really get that definition, but you know, I'll just kind of hang in there for now, and once we get past this material, I'll finally be good. And I'll be ready come chapter 3 to start fresh. If you're even tempted a little bit by that thinking, did I not start the lecture? It's going. Okay. If you're tempted even a little bit by that thinking, we need to correct it now. Because everything we talk about in this class is limits. And that's the one definition that you for sure need to get your head wrapped completely around. Limits. You're going to say that we define continuity in terms of limits. A derivative is just a type of limit. An integral is just a type of limit. So it's all limits. So you need to wrap your head around limits. You need to make sure you understand that epsilon-delta definition and that you can use it as needed. Make sense?
Yeah.
So hang in there on those. Read and reread that definition until it is just clear to you exactly what it's saying. Okay, continuity. Continuity, we already gave you the intuitive sense of what continuity is. A function's continuous if I can draw it without picking up my writing utensil. If I have to pick up my writing utensil where I have to pick up my writing utensil, it's not continuous at that point. Go ahead.
So like in that example right there, that you would say that that isn't continuous, right? But
well, we say it's not continuous at points.
Yeah.
So we say that the function is not continuous at 1, not continuous at 2, and not continuous at 4.
But it is continuous elsewhere. Like
Right, it's continuous right here, it's continuous right here, it's continuous here, 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 here.
Okay.
And then we'll notice, what about at 1?
Not continuous.
It's not continuous, but notice if you approach it from the left, it is continuous as we approach 1 from the left.
From the left?
Uh-huh.
Yeah.
So as we approach 1 from the left,
Isn't
we're
that from the
continuous.
right?
From the right, thank you. Going left. If we approach it from the right, we're continuous. And if we, for example, at this 1 as well, if we approach this 1 from the left, we're also continuous there. Up to and including that point. So we're going to come up with notions that capture this intuition. So let's get the exact definition now. A function is continuous at some point c, provided that the limit as x approaches c of f of x is equal to f of c. So I'll pick a point where we know this function is continuous, 3. The function is continuous at 3 because the limit as x approaches 3 is what?
3.
2.
Oh, 2.
The limit as x approaches 3, so 3 is going to be our stand-in for c here. 3 of f of x, if this function here is f of x, is equal to 2, which is equal to f of 3.
Okay, I see it.
You see what this is saying now?
Yep.
The limit as x approaches the point is equal to the value of the function at that point. Does that make sense?
Yeah, it does.
Yeah. So continuity, pretty easy to understand if you understand this portion. It's just saying the limit exists, and furthermore, the limit is the value of the function at that point. So in order for a function to be continuous at a point, you need 3 things, roughly speaking. You need A, the function to be defined at that point, B, the limit to exist at that point, and C, the limit to equal the value of the function at that point. Make sense?
For both
Yeah.
sides.
Yeah, just limit, not limit from the left to right. Okay. So let's read this again. A function is continuous at C, provided that the limit as x approaches C of f of x is equal to f of C, and continuous from the right / left, depending on which one you're talking about, provided that the limit as x approaches C from the right or the left is equal to the value of the function at that point. So, if we look at 0 here, the function is not continuous at 0. The function is continuous at 0 from the right.
Okay.
Good? What about at 1? Are we continuous at 1 from the right?
Yeah.
Are we continuous at 1 from the left?
No.
We're not continuous as we approach the scene from the left?
We are continuous.
Are we or are we not?
I don't think so.
As we approach it from the left, do we get closer and closer to the value of the function at that point?
Yes.
No, we're going
No,
down.
we don't.
We're not coming up towards 1.
Well, oh, I see.
So from the right, yes. From the left, no.
So, okay. I get you.
You see what this is saying now?
Mm-hmm.
We would have to have the limit as x approaches 1 from the left of f of x equal to f of 1. That is not the case when we approach from the left. It is the case when we approach from the right. Make sense?
Yes.
Yeah.
Okay, so those are the 3 different types of continuity we'll talk about. Continuous at a point, continuous from the left at a point, continuous from the right at a point. I think you understand the definition now. Okay, let's go back and look at this function. What is this function? Describe it to me geometrically.
I don't remember. Wait, isn't it the circle?
It's half a circle.
Half a circle.
It's the top half of the circle.
Yep.
Remember, a function can't ever give you a circle because it doesn't pass a vertical line test. And it's a circle with radius. What's the radius?
Just 1.
Let's rewrite this as the same thing as y is equal to the square root of 4 minus x squared. Square both sides, we get y squared is equal to 4 minus x squared. Move the x to the other side. X squared plus y squared is equal to 2 squared. What's the radius of the circle?
2.
2, right? It's the set of all the points that satisfy the Pythagorean theorem when your hypotenuse is 2.
Okay.
So all the xy points, distance 2 from here,
Why does,
but only looking at the positives.
in that format, why does it make a full circle, but when you put a root on it, it becomes half a circle? Like, it seems like just by rearranging.
Because when we go backwards, when I go from here to here and I take the square root, I have to do plus or minus. The positive one's up here, the negative one's down here.
And that works. So it's just interesting that the different arrangement of the formula produces a different result on the graph.
It comes from the fact that when you take a square root, you can have both positive and negative results. The square root of 9 is both 3 and negative 3. Well, that's not true. If I write square root of 9, then that is equal to 3, because when we use square root, we're always talking about the positive number. We talk about that as a function. But when I talk about what are all the solutions to x squared equals 9, now I'm talking about plus or minus 3. So if x squared equals 9, then x is equal to plus or minus the square root of 9. Or in other words, plus or minus 3.
Right, but you're saying it doesn't go the other way around. The square root of 9 is not plus or minus 3.
If you have 3, when you square it, you get 9. If you take the square root of 9, if you look for the value such that when you square it, you get 9, now there's 2.
Right.
Here we just have a particular, the top half of the circle. Anyways, so we got top half of a circle, like this, Where is the function continuous?
Everywhere except at the 2 points, right?
everywhere, tell me the points where it's continuous. What does this look like roughly? Draw. Ooh, that was terrible. Smooth this up. This point right here is 2. This is -2. Where is the function continuous?
From -2 to 2?
It's continuous -2 to 2, open interval, not including the endpoints.
Okay.
And then it is left-hand continuous here, or what do we call it?
Right.
Continuous from the right here, thank you, and continuous from the left here.
So why?
At those actual points. Here's where it's just plain old continuous, everywhere in between.
Do you have any notation or anything to show if it's continuous from the left or from the right? Or do you equal?
No, just this. Plus, if we're talking about taking the limit from the left, or from the right, negative if we're talking about taking it from the left.
Okay.
Okay. Another example. Look at this function. Where is this function continuous?
Infinity to 0, open interval, and 0 to infinity.
So it's continuous everywhere except 0. And then at 0, it's what?
Continuous from the right.
Continuous from the right.
Okay, I see that.
Wonderful. Okay, let's look at another function. This is the floor function, the round down function. So what does this function look like if we go to plot it? Well, if I plug in 0, what do I get?
0.
0. If I plug in 1/2, what do I get?
0.
0. If I plug in a number barely smaller than 1, what do I get?
0.
0. Okay, if I actually plug in 1, what do I get? 1. If I plug in 1.5, what do I get?
1.
1. If I plug in a number barely smaller than 2, what do I get?
Same thing.
And so now, hopefully it makes sense to you that this picture looks like this.
Okay.
My drawing might be a little off, but I think you get the point, right?
Yeah.
Where is this function continuous? It's continuous on any interval n to n plus 1, where n is any integer,
Okay.
right? It's continuous on any open interval between the integers.
You're going to include the intermediate bracket on the left, right?
No, not including. Open parenthesis.
No.
For continuous.
On the left. Wait.
This is
No,
not
open
left.
parenthesis. This is full continuous. On top of that, it is left-hand continuous, or continuous from the right, sorry. It is continuous from the right at every integer n. So it's continuous from the right at every integer n, and it's just regular continuous on every open interval n to n plus 1.
So if we get this on our homework, how would we write out that answer?
Where is it continuous?
Yeah. You would say that, and then would you just write in words, it's also continuous. from-
Explaining in words is just fine.
Okay.
We won't come up with dense notation. Just put it in words. If you can come up with a way to express it as a set, that's fine too. I'm not saying don't do that. I just don't want to require you to have to think about it that way, because the point is you get where it's continuous, not can you express it as a set. Okay. So let's look at some functions and talk about whether they're continuous or discontinuous. So first off, A. A, just a line that comes straight through. Is that function continuous?
Yeah.
Yes. Okay, B. B, that same line, except for now at this point we jump it up here.
No.
No, it's not continuous at that point. And we call that point a, lost the terminology he uses, a removable discontinuity. So this right here we call a removable discontinuity.
Okay. So the whole function is called discontinuous, right? And you're saying
If we're saying, is the whole function continuous, the answer is no. Because when you say the whole function, you mean continuous at every point.
Yeah.
Is the whole function continuous? No. Is the function continuous on this interval? Yes. Is it continuous on this interval? Yes. Now, this function has a, lost that terminology again, a removable discontinuity at 0 when the point's out, somewhere else. Good there? Now let's look at it when we don't have that point. I thought that was one of the pictures. Worth explaining anyway, so let's say that we now have it look like this. Is that function discontinuous anywhere?
Discontinuous
Yeah.
anywhere? Yeah.
Is that function continuous?
No.
Let's ask that. Now it is continuous. Yes, because that point is not in its domain. For every point in its domain now, what is the domain of the function? The domain of the function is negative infinity to 0, union 0 to infinity. That is its domain.
Why?
Is it continuous at all those points?
Yeah.
Yes. We didn't give the function value at the point. Notice over here, we always had an actual value for the point. Oh, I lied. 2. I lied to you at 2.
So 2 is continuous?
It's not continuous at 2 because 2 is not in the domain.
Oh.
So it's not discontinuous at 2 either. 2 wasn't in the domain of this function. I wonder if I drew that wrong and it's supposed to have a point somewhere like up here. Let's pretend it did have a point up here. So
Well,
we
it's
get the
nice
point.
to give us an example of it not having a point and what to do with it.
Right, so when the point's up there, it's, if I put the point here, it is now discontinuous at 0, and it has a removable discontinuity. If I get rid of that point, so that was never in the domain, now the function is continuous.
The whole function.
Even though
The
there's no
whole
point.
function is continuous.
Even though there's no.
It is continuous at every point in its domain.
But
Yes, that makes sense.
Oh, I see.
when the limit. How does that follow the definition? Of the limit of x as it approaches 0. left
For
x
any
equals
point
left.
C where the function's defined. We can't say that this function has a limit as x approaches 2. It doesn't. 2 is not in the domain. We're not trying to say it's continuous at, oh sorry, not 2, 0.
I don't think
We
it
don't say the
follows-
function's continuous at 0 because 0 is not in the domain.
But
That's
it-
the only place that you could say it isn't continuous, right?
So what if
Obviously it's continuous everywhere except 0, right? Continuous here, 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 here. You with me?
Yeah.
The only place it could possibly not be continuous is at 0.
Making.
But the function isn't defined at 0. 0 is not in its domain. So the function is continuous. What do we mean by continuous function? A function is continuous if it is continuous at every point in its domain.
Okay.
So since the domain doesn't include that point,
what do you do if there is a point?
then it's discontinuous. And it's a removable discontinuity. Why is it a removable discontinuity? Because when we remove it, the function is now continuous.
How does that look in the definition of continuity that you put there? Continuous.
So here's our definition for continuous, right?
Yeah.
This is continuous at a point C. What C are you saying this is discontinuous at?
0.
0. We can't do 0. That's not in the domain. We can't talk about f of 0.
So you can't. It says it's continuous if that happens. If that doesn't happen, why does that still?
It is continuous at a point C if this happens.
Mm-hmm.
Okay, so if this happens, it's continuous at that point.
But it's
Here's its domain. Pick any one of these points, and this is true. You're wanting to pick 0. 0 isn't in the domain. You can't pick 0. The function is continuous on its whole domain. Pick any point in its domain. The function is continuous at that point. Go ahead.
I think he's having problems because it's not following the intuition you gave us of lifting up your pencil.
Okay, so that was basic intuition for where the function is continuous on an interval. Notice that on this interval of the domain, that's the case. Notice on this interval of the domain, that's the case. So break your domain down into all its intervals, and then that intuition should still hold.
Okay.
In fact, there's no brackets, meaning not up to a specific value.
Right, not including 0. We didn't include 0 in there, because it's not square brackets. Okay? So it's called a removable discontinuity when we put the point in there. A removable discontinuity because if you get rid of that point, the function is now continuous.
There's lots of points, it's still removable discontinuity.
It needs to be a single point like this. So discontinuous, I erase that point, so the function is no longer defined as 0. Now it's continuous. continuous on its domain. We just changed what the domain was. We took 0 out of the domain.
Okay.
We got rid of the bad point. Okay. Let's look at C. CE obviously isn't continuous at 0. And then not only is it not continuous at 0, but it jumps at 0. And we call this a jump discontinuity.
Yeah.
Pretty obvious. Why we call it a jump discontinuity? Think that makes sense. Okay, more interesting one. Here's looking at something like 1 over x squared. So this is roughly 1 over x squared. My picture's lying, but close enough. And what's happening is, as we get closer and closer to 0, this thing shoots up to infinity. And as we get closer and closer to 0, this thing shoots up to infinity. So at 0, the function isn't continuous. Notice you can't plug 0 into that, otherwise you'd be dividing by 0.
Okay.
So a discontinuity like this we call an infinite discontinuity.
Why is that discontinuity? Why?
Does this all have to do with?
If it goes to
That's
any
a good
number,
point.
it keeps getting closer.
Because
and
0
closer to
isn't in the
0.
domain.
Yeah, doesn't it follow the same as the B?
But it's also not approaching an actual number.
It's
But for any number in the domain, we could approach it from the left and from the right. I wonder if I was supposed to plug in a point. Okay, so it's just a name for it. So they're just saying if at a point it has a right-hand sided limit and a left-hand sided limit, but those go to different values, but those go to infinite values, then we call it an infinite discontinuity. So just a name. The function would still be considered a continuous function on its domain. Picking a point in the domain, and it would still be continuous at that point.
yeah.
So I guess it's just a name, which is kind of confusing.
But it is a continuous function.
It's continuous everywhere on its domain. Yep.
You're saying that the whole thing is discontinuous?
I'm saying that we call 0 an infinite discontinuity at the point 0,
So the
because
function-
as the function approaches that point, it shoots off to infinity.
Yeah.
Okay, last one the author talks about is an oscillating discontinuity. Now this is a really weird function that there's no chance of me really drawing, so you just need to get a feel for what it's doing. Now notice that as we plug in really, really small values for x into this, then the sign of then 1 over x gets really, really big, right? If I go from 0.01 to 0.001 in this function, so if I go from 0.1, which is like right here, to 0.001, which is right next to it, so teeny tiny distance I move, right? How much did my value of the function change? The value when I plug that in for here, 1 over x then goes from 100 to 1,000. And if I plug 100 into the sine function and I plug 1,000 into the sine function, how many waves does that make? Remember, the sine function goes up and down every 2 pi, right? So roughly every 6.28, the sine function goes up and down. So from 100 to 1,000, in 900, how many times does it go up and down? A lot. So going from this point to this point, I'd have to draw lines going back and forth a ton of times, which obviously I can't do. So this is getting really, really, really cramped-packed, oscillating faster and faster the closer we get to 0. Same thing happens as we approach from the negative side of 0. So this function actually is discontinuous at the value 0. Oh, but we have the same type of thing. 0 isn't in there.
So the whole function is continuous.
So the function's continuous on its domain, but the limit as the function approaches 0 doesn't exist on this, from the left or the right. You can't say it's approaching 1, you can't say it's approaching 0,
Okay.
because it's blowing up. It's oscillating back and forth, back and forth, back and forth.
Well, I imagine it's just undefined at that point.
No,
1 divided by 0 is not undefined.
well, we're not saying at 0, we're saying as it approaches 0. What does this thing do as sign approaches 0? It just oscillates back and forth really, really fast. It gets arbitrarily close to any number you want. The output keeps getting 1 as many times as you want, it keeps getting -1 as many times as you want, and every value in between. So it's not approaching a single number. The function isn't approaching a single number as x approaches 0. Make sense?
Mm-hmm.
So it's like they just decided that was
It's not approaching a number. Notice that when I talk about this, the limit as x approaches -1 here is whatever this value is. The limit as x approaches 0, it's oscillating up and down. You can't say it's getting closer and closer to one number.
Yeah, but any number you plug in, you can get a finite output, a single output. No matter how tiny.
Going back to our definition of what a limit is, for any epsilon I choose, so I pick an epsilon that's less than 1 to -1. So here's 1, here's -1. I choose my epsilon, you pick a point, doesn't matter. You say, okay, this has a limit going to a point, pick whatever point you want, doesn't matter. You say that point. I pick my epsilon around that point. Now for any delta you pick around 0, you will pick points whose output goes to 1. You can't keep them inside of that, because it oscillates an infinite amount of times in this space, however small you make that space. So it breaks the definition of a limit. So this does not have a limit as it approaches 0. Any point you pick, I can break it. Okay, so question now, is f of x equal to 1 over x continuous? Roughly, what does this picture look like? Looks like this, looks like this. Is that a continuous function?
Mm-hmm.
Yeah.
Yes, it's continuous everywhere on its domain. It has an infinite discontinuity at 0, I guess we'd say, but it's still a continuous function, just a name for its behavior as 0. Okay. Now, some basic theorems for continuous functions that we already had for limits. Basically, our theorems for limits also hold when we're talking about continuous functions, so these will all look familiar. Let's go over them. If f and g are continuous at some point x equal to c, then so are the following. F plus g is continuous, f minus g is continuous, a constant times f is continuous, where k is a constant. The product of two continuous functions is continuous. The quotient of two continuous functions is continuous, provided that the bottom function isn't 0 at the point where you're saying it's continuous. F to the n, where n is a positive integer, would be continuous at that point. And then the nth root of f would also be continuous at that point. So let's make sense of this one more time. I have f and g, two functions. What do I know about those functions? They are continuous at the point c. If that's the case, then I know f plus g is continuous to c, I know f minus g is continuous to c, I know some constant times f is continuous to c, etc., etc., etc.
Okay.
The exact same rules that we had for limits.
Is that times or like?
This is times.
Oh, gotcha.
Yeah, sorry, not open dot, not composed, times. Now, notice that since continuity is defined using a limit, when you talk about continuous functions, you're just talking about limits. So all these rules about continuous functions you get for free from the rules we already had about limits. So when we prove one of these, you prove almost all of these the exact same. You just use its corresponding limit rule. But we'll do a proof of one of these to get a sense for how we basically just get this for free from what we already know about limits. So we'll just do the top one. So if the limit as x approaches c of f of x is equal to f of c, or in other words, if f is continuous at c, that's what this says. if f is continuous at C, notice our definition of continuity right here. So if f is continuous at C and g is continuous at C, then f plus g is continuous at C. This is saying f plus g is continuous at C. You with me?
Yep.
Here's what we're trying to prove. Trying to prove if this is true and this is true, then this is also true. That's what I'm going to prove. Okay. So observe that the limit as x approaches C of f plus g of x, we already have definition for this notation. What do we mean by f plus g of x? We meant f of x plus g of x. Right? That's what it means to add two functions together. You do that. Now we know from our limit rules that the limit of a sum is equal to the sum of the limits. So the limit of a sum of two functions is equal to the sum of the limit of the two functions. You with me?
Yep.
Okay. Well, what is the limit as x approaches C of f of x? F of C. And what is the limit as x approaches C of g of x? It's g of C. And then f of C plus g of C is exactly what we mean by the notation f plus g of C. So, small little one-line proof. And now hopefully you see how you can prove basically any of these. The whole heart of the proof is going from this line to this line. Going from here to here. That's the heart of the proof, just realizing the limit of the sum is the sum of the limits. If I were doing this one, then the heart of my proof would be the limit of a difference is the difference of the limits. If I were doing this proof, I'd be using the fact that the limit of a product is the product of the limits. So all the proofs are basically the same. And it's just using the corresponding limit rule. Make sense?
Yeah.
Okay. So, moving on. Polynomials. You remember what a polynomial is, right?
Yeah.
P of x is equal to some number times x to the n plus some number times x to the n minus 1 plus all the way down. Polynomial. Now, we already did, back when we were talking about limits, we showed how the limit as x approaches c of some polynomial is what you get when you just plug in that point. Now, in case I'm losing you in that notation, let's come down and do this one really quick, just to make it instantly quick. Look at this function right here. This is a polynomial, right?
Yeah.
What is the limit of this polynomial as x approaches 2? What are you doing in your head? You're saying it's 2 squared plus 4 times 2 minus 5, right?
Yeah.
Yeah.
That's what you were doing in your head. The point is you just plugged in the point, because it's a polynomial.
Yeah.
That's what we're saying up here. The limit as x approaches c of a polynomial, p of x, is just p of c. Just plug in the point.
Yep.
You with me?
Yes.
Now, since this is the case, notice then, what does it say? If I know that for any polynomial, the limit as x approaches c of p of x is p of c, what does that tell me?
It's continuous.
That it's continuous at c. So we also now know that any polynomial is continuous at a point c.
Okay.
So a function like this is continuous everywhere.
Okay.
Make sense?
Mhm.
Similarly, we talked about rational functions. So we said if p of x and q of x are polynomials, then p of x over q of x is continuous everywhere, as long as q of c is not equal to 0. So it's continuous at any point c, as long as q of c isn't 0. Because we also showed that this is true with rational functions. We showed that the limit as x approaches c of p of x over q of x is equal to p of c over q of c, as long as q of c is not equal to 0, right? This is the same thing as saying it's continuous there, as long as QC is not 0. So when you have a rational function, a polynomial over a polynomial, you already know it's for sure continuous everywhere where the domain, or where the denominator isn't 0. So when we talk about its natural domain, it's going to be continuous everywhere. So if I say x squared plus 2 minus 5 over x squared plus 1, where is that function continuous?
Everywhere.
Everywhere, because the domain can never be 0.
Okay.
What if I put a minus 1 in here?
It's everywhere except
Can't be
negative
a
1.
Then everywhere except for plus and minus 1. Make sense? Okay. Alright, let's show that f of x equal to the absolute value function x is continuous now. Now one way we could rewrite the absolute value function is absolute value of x we can say is equal to x if x is greater than 0, 0 if x is equal to 0, and negative x if x is less than 0. You with me? Perfectly valid way to define the absolute value function. Am I losing you on that?
Where's negative x?
Right there?
I mean,
Oh, let's do an example. Okay. Plug negative 3 into this function. So the absolute value of negative 3, what's that equal to? Well, is 3 greater than 0, or is negative 3 greater than 0?
no.
So we're not using this line. Is negative 3 equal to 0?
No.
So we're not using this line. Is negative 3 less than 0?
Yeah.
So the answer is negative 3,
Okay.
which is equal to 3. Clicking. So this definition now makes sense for absolute value?
Yeah.
Awesome. So now, let's show it's continuous. Everywhere. First off, how do I know it's continuous from 0 to infinity? Like that. These are all the positive numbers. How do I know it's continuous for every positive number?
Because they just equal x if they're in there.
Because it's just x if it's a positive number. And x is a polynomial.
Oh, okay.
Okay, how do I know it's continuous on this interval? Negative 0 to negative infinity. Negative 0 is just 0.
I
Alright.
mean, negative infinity to 0.
Oh, thank you. Negative infinity to 0. Yes.
Because it's just negative x. And that's a polynomial.
And that's polynomial, so continuous. So the only place that we need to argue now is what about at 0? Right?
Yeah.
So let's look at this. What is the limit as x approaches 0 from the right of the absolute value of x?
0.
0.
0, right? What is the limit as x approaches 0 from the left of the absolute value of x?
Same thing.
Still just 0. Notice that when we're saying what does it approach from the right, we're just looking at what this function gets closer and closer to as x approaches 0, so you can just plug in 0. Right? Similarly with this one, just plug in 0, we get negative 0, which is still just 0. Put the equals there. So the right hand and left hand limit both equal the same thing, so that's what the limit equals. So now I know the limit as x approaches 0 of absolute value of x is equal to 0, but that's also equal to the absolute value of 0. Or f at that point. So it's continuous at that point. Notice what continuity is. Is the limit as x approaches that number of our function equal to the value of our function at that number? Is the limit as x approaches 0 of absolute value of x equal to absolute value of 0?
Yeah.
Yes, so it's continuous at that point.
So why exactly is it not included in the domain?
It is. So this is continuous everywhere. It's continuous on all our. I just showed it one piece at a time. I showed why all these are continuous points, why all these are continuous points, and then why 0 is a continuous point. Good?
Yeah.
Okay. So next, function composition also maintains continuity. So what do we mean there? If f is a continuous function, if f is continuous at some point c, And if g is continuous at some point f of c, then g composed with f is continuous at c. So let's draw the picture here to make sure we understand. Here's c. F takes c and maps it to f of c in a continuous way. With me? And then g, we know, takes f of c and maps it to g of f of c in a continuous way. That was given. If I know that this is happening continuously, and I know that this is happening continuously, then I know g composed with f is mapping c to g of f of c in a continuous way. The function composition is continuous.
Okay.
Good? Some intuition for this. Since f is continuous, then x being close to c implies f of x is close to f of c. Right? What does continuity maintain? It maintains that the points that are close are still staying close in the mapping.
Just like continuity and topology.
Exact same thing. Everything that we're talking about, continuity here, is continuity in topology.
Yeah.
Topology can just talk about continuity outside of just the real numbers. Here we're always restricting ourselves to the standard topology on the real numbers.
Okay, I see that.
But it's the exact same math. And we're talking about the exact same things. Yes? So, since x close to c implies f of x is close to f of c, remember that ultimately our definition for a limit comes back to something that looks like this. Am I still on the camera over here? How far over can I go?
You know, off the camera.
Okay, where can I scribble that I can see? I'll scribble over here. Okay, so we already know that x minus c less than delta implies f of x minus f of c less than epsilon. Right? This is what a limit maintains. It maintains that if x is close to c, then f of x is close to f of c.
Okay.
Right?
Yeah.
Sorry, it just says L for our limit point. If we're saying continuous, then it just switches it to this. So in general, you're used to seeing it like this, L. This is saying that a function's limit is L. If we want to say the function's continuous, it's just switching that L with an f of c. That's all continuity says. It says the limit at that point is just f of c instead of some random L. Right? That's the only difference between what you see here and when we say the limit as x approaches c of f of x is equal to L. This and this, the only difference is we replace our L with an f of c. So when we're talking about a function being continuous at a point, it means this is true. Replace the L with an f of c. And that, by the way, is why I accidentally call it the Epsilon-Delta definition of continuity. Because the only way that you change that definition to be talking about limits, to talk about continuity, is replace the L with f of c. And so in topology, we actually did it like this, and we called it the Epsilon-Delta definition of continuity. So the way that you prove a limit is a value, and the way you prove that a function is continuous at a point is the exact same thing. You just replace the L with f of c, the function value at that point. Make sense?
Yeah.
Okay, so this is what it means to be continuous at a point. This holds. So now, with that intuition, what does it say? X being close to c implies f of x is close to f of c. That's a high level what that says. So now, to try and give you intuition for why this works, let's make sense of it. Since f is continuous, then x being close to c implies f of x is close to f of c. With me so far? Now, since g is continuous, then f of x being close to f of c, these are now the inputs to g, implies g of f of x is close to g of f of c. You follow that? So, put the whole thing together. X being close to c implies g of f of x is close to g of f of c. So the composition is continuous. Am I losing you in that? A little bit? A little bit. let's, I'll just erase right here and we'll draw all these out really quick. So since f is continuous, I know that if x, what do we do first? Is it c minus x or x minus c? X minus c?
Yeah.
So I know that x being close to c implies f of x is close to f of c. Right?
Yeah.
Now, I know since g is continuous, then g, my input for g is going to be f of x and f of c. So f of x minus f of g, if, not f of g, sorry,
F of C.
f of c, thank you. Those being close together implies some other value, g, running out of space to write, implies, I'll put down here, implies the absolute value of g of f of x minus g of f of c is also close together. I'll just call it epsilon 1. So x being close to c implies g of f of x is close to g of f of c. That's what we're saying. This is just intuition for why function composition keeps the function continuous. It keeps the points close, that we're already close.
Okay.
That's all we're saying. Okay, so intuition. Okay, continuous on natural domains. Let's look at each of these and argue why we know that these functions are continuous on their natural domains and how we might argue that. With me?
Mm-hmm.
Okay. So, let's look at this function really quick. How could we re-express this function if we say that f of x is equal to x squared minus 2x minus 5, and we say g of x is equal to the square root of x? Then notice now this function is g composed with f of x.
Yeah.
Yeah.
You with me on that? Now is f of x continuous?
Yeah.
Yeah? Is g of x continuous?
Mm-hmm.
Square root function?
No. Yes.
I don't know.
Yeah, it is.
Square root function.
It's continuous. Yep. Maybe we need to specify it's only continuous from the right at 0,
Right.
Okay.
but continuous. So function composition maintains continuity. So when you compose the both of them together, you end up with something that's continuous on its natural domain, whatever its domain is. Make sense?
Yeah.
The whole point here is maybe you're looking at a function that's kind of complex and you're not sure how to determine whether or not it's continuous. But maybe you can view it as a couple functions composed together that are more obvious for you. That's the whole point here. So maybe that is a bit much for you to take it in one go, but you can look at that and say yes for sure, and you can look at that and say yes for sure. Put those together, continuity maintains, or composition maintains continuity. Put them together, your thing's still continuous. That's the point.
Okay.
Make sense?
Yeah.
Yeah.
Okay, so let's look at another one. What about this beast right here?
Are you asking us whether it's continuous or not?
Yeah, how might we want to justify that this thing's continuous?
Divide the two different functions. So x and 2/3 is f of x, and 1 plus x4 is g of x.
Yeah, we might say f of x we'll say is equal to x squared, which we know is continuous. G of x we'll say is equal to x to the 1/3 or cube root, which we know is continuous. How did we know the roots are continuous, by the way? I'm just referencing these rules over here, so we know this one.
Oh.
That's how we knew square root. Sorry, I should have been more clear on that. So we knew square root from before. Now we know cube root and we know x squared. Those are both continuous, right? And then we might also say our final one is going to be let me think how I want to do this. Well, then we can just look at this one. I don't need to write all these out. I think you'll get it. So right here we have squaring a cubed root, or cubing a square root, squaring a cubed root, or taking the cubed root of a square, however you want to think about it. You can view this as x squared to the 1/3 if you want, right? The point is, okay, that's a composition of two continuous things. So the numerator is continuous, right?
Okay.
The denominator is continuous. And we know that division of continuous is continuous, provided the denominator is not 0.
How do we know? Oh, never mind.
Good?
Yep.
Yeah.
Okay, let's justify the next one. Looking just on the inside real quick, is the numerator continuous?
Mm-hmm.
Yeah.
Yep. What about the denominator?
Mm-hmm.
What if the numerator's 2?
What if it's just 2?
No, the denominator is.
Is the denominator continuous?
Yes.
Except where?
Except where x squared equals 2.
Except for plus or minus root 2,
Mm-hmm.
right? Because you plug in root 2 to this, you get 0.
Yeah.
So continuous everywhere except for plus or minus root 2, just looking at the inside. Now we can do the inside. If I say f of x is equal to x minus 2 over x squared minus 2, and then I say g of x is equal to absolute value of x, compose those together, we get this.
Okay.
We already proved that the absolute value of x is continuous. Function composition maintains continuity, so the whole thing is continuous except at negative root 2 and positive root 2. It's continuous on its natural domain. Good?
Yeah.
All right, next one. Let's look at this beast. Is this thing continuous?
Yeah. Can't you just do the same thing you did to C?
Pretty close. Is x continuous
Yeah.
by itself? Yeah. Is a sine continuous?
Yeah.
You might remember the graph of a sine function looks like this.
Okay.
On forever. So x is continuous, sine of x is continuous, therefore the product's continuous, the denominator's continuous, therefore the function's continuous, or therefore the fraction's continuous. And then take the absolute value, still continuous. Good? Okay, so I'll give you some sense for how we can tell things are continuous and where they're continuous. And it pretty much follows intuition there, I think. Okay, now if g is continuous at some point b, and the limit as x approaches c of f of x is equal to b, so notice b is an output for f, but an input for g. We're going to be doing function composition. So if g is continuous at some point b, and the limit as x approaches c of f of x is equal to b, then the limit as x approaches c of g of f of x is equal to, g of b is equal to g of the limit as x approaches c of f of x. That's what we're going to prove. In other words, we're going to prove that you can move limits inside functions. If I've got a limit of g of a function, then that's the same as g as the limit of the function.
Gotcha.
So we're going to prove that you can move that limit inside the function.
Okay.
Does that make sense?
Mm-hmm.
Okay. So let's prove it. Let epsilon greater than 0 be given. Some positive number. We don't know what it is. Now, since g is continuous at b, then what does that mean? That means for any epsilon, there must exist some delta, call it delta 1, such that if y, the input to g, I'm just using y for the input to g and x for the input to f. So don't get confused by the y here. So y is just my input for g. So if my input for g minus b is less than delta, g of y minus g of b is less than epsilon. Let's say this again. What do I know? I know that g is continuous at some point b. What does that mean? That means that for any epsilon you choose, there must exist some delta 1, such that if y is within delta 1 of b, then g of y is within epsilon of g of b. That's what it means for g to be continuous at b. It's just a definition. Make sense so far? It's a dense definition. I'm telling you, it's not going away. So you got to wrap your head around that limit definition. It's here to stay forever. Okay. So since the limit as x approaches c of f of x is equal to b, I know that this limit is true. That was given, right? Well, what does that mean? If the limit as x approaches c of f of x is equal to b, that means that there must exist some delta such that if x is within delta of c, f of x is within delta 1 of b. Let me restate this. So let's come back up to here for g. So let epsilon greater than 0 be given. I know that g is continuous at b. That means for any positive number you choose, namely epsilon, there must exist some delta 1 such that y being within delta 1 of b, then g of y is within epsilon of g of b. I'm choosing the variables here. There's nothing special about delta 1 and epsilon. Those are just positive numbers. Now, since I know the limit as x approaches c of f of x is equal to b, then for any positive number you choose, namely delta 1, I can find some number, namely delta, such that if x is within delta of c, then f of x is within delta 1 of b.
Why do you choose delta 1, or does that not matter?
It's just the name of a variable.
I'm saying,
Delta 1 is going to end up disappearing when I combine all these together.
okay.
So it's my weird one. So then, put all those together, what do I know? I know that if x minus c is less than delta,
Yeah.
if x minus c is less than delta, then that means f of x minus b is less than delta 1.
What's the difference between delta and delta 1?
They're just two different positive numbers. The same way that I might use x sub 1 for one number and x sub 2 for another. Okay, so I know that if x minus c is less than delta, then f of x minus b is less than delta 1. And I know that if f of x, or y, minus b is less than delta 1, then g of f of x, or g of y, is less than g of b. Sorry, then g of y minus g of b is less than epsilon, which is what I have written here. So this being true implies this is true. This being true implies this is true. This being true implies this is true, which is this.
Why do you switch out the f of x for y again?
Just to try and keep it clear, I didn't want to make this too messy right out the door.
Gotcha.
I could have done that from the beginning. I could have said all my g's inputs are f's outputs, if I want to. But technically, g can handle things that aren't necessarily coming from f.
That's right.
So if this is true for all the inputs g happens to take, it's true for the inputs g gets from f. Good?
Yeah.
So x being within delta of c ultimately implies g of f of x is within epsilon of g of b. So, what does that mean? That means the limit of g of f of x as x approaches c is g of b. That means that the limit as x approaches c of g of f of x is equal to g of b. And g of b is the exact same thing as g of the limit as x approaches c of f of x. So I just barely showed this line right here, which is what we were trying to show. Go ahead.
In what you're trying to prove, you say g of b, and that the limit as x approaches c of g of f of x is equal to that, right? Oh, I see it now, sorry.
Yeah, look at this whole line. That's what we showed.
I was just saying that the limit of f of x is equal to b, and I just didn't see the g.
Yep, the limit of f of x is equal to b. Good?
Yeah.
Okay. So we can move limits inside of functions. Perfectly valid thing to do. Well, where might we want to do something like that? Let's look at that problem up there. Let's look at the limit as x approaches pi halves of that whole thing. Cosine of 2x plus sine of 3 pi halves plus x. And let's take the limit as x approaches pi halves. Now, if I gave that problem to you before, you might have been a little bit confused. Where do I even start? Now it's easy. This is the same thing as the cosine of the limit like that, right? We can move the limit inside. Now the limit of a sum is the sum of the limits.
Yep.
So this is the same thing as cosine of the limit as x approaches pi halves of 2x like that. And now we can take each of those separate limits. Didn't leave myself a lot of space here, but I think you see the process happening now. So ultimately, what are we going to get? We're going to get cosine of, what's the limit as pi halves, as x approaches pi halves of 2x?
0.
What is the limit as x approaches pi halves of 2x?
That's pi.
It's just pi.
Why? What?
We're just looking at the function now, 2x. What is the limit as x approaches pi halves of 2x? 2x is just a polynomial. So it's going to be equal to 2 pi halves,
Okay,
which is equal to pi. So we're going to get cosine of pi plus that other part, the limit as x approaches pi halves of sine of that whole thing, is the same thing as we can move the limit inside and take the limit on the inside. What's the limit as x approaches pi halves of that inside of that thing? Of 3 pi halves plus x.
Just
4 pi halves? Or
4 pi
2
halves or 2 pi, right? So this is cosine of pi plus sine of 2 pi. With me?
Yeah.
What's sine of 2 pi?
0.
0. What's pi plus 0? Pi. What's cosine of pi? -1.
okay. That's
So the
great.
limit as x approaches pi halves of that whole thing is -1. Think you got it?
I mean, I think it would be nice if we had another example.
Couldn't you just start that problem by replacing all the x's with pi half?
Yes, that's the whole point of the exercise. So yeah, I never want to see you actually go through all that work again anymore. The point is, you don't need to do all that. So yes, we could have replaced all our x's with pi halves and been perfectly fine.
Okay.
Make sense?
That's easy.
Yeah. Just make sure you understand why.
Yeah.
Yeah. Okay. Next we'll talk about what is called the intermediate value theorem, IVT, intermediate value theorem. It's a pretty intuitive theorem. Let's make sense of it. What does it say? It says if f of x is a function that is continuous on a closed interval, a to b, so a to b is a closed interval, it includes its endpoints, and if y naught is any value between f of a and f of b, so our function might look something like this. Here's some function. Here's a, here's b. A to b, that's a closed interval. Here's a function that's continuous on the closed interval, right?
Yeah.
F of a is just a value of the function at a. F of b is just a value of the function at b. With me so far?
Yeah.
So what does the intermediate value theorem say? It says, pick any value y naught between f of a and f of b. Doesn't matter what value you pick some value between them, call it y naught.
What does y not mean?
It's just a variable. We're just calling it y naught. Pick some number, call it y naught between f of a and f of b. What's y naught? It's just a number between f of a and f of b.
Because why not?
Because why not? Oh, sorry, I always read y sub 0, why not? That's a consequence from physics. Anyways, pick some number between f of a and f of b. Doesn't matter what it is. The intermediate value theorem says, then, if you pick any number between them, I'll move this over here, then there must exist some point in the domain, in the interval C, some point in the interval between A and B, call it C, such that f of C is equal to y naught.
Okay,
It's pretty straightforward. So let's read the whole thing one more time and make sure it makes sense with this picture. If f of x is continuous on a closed interval AB, and if y naught is any value between f of A and f of B, then there exists some C in the closed interval AB such that f of C is equal to y naught. Does everyone feel like they got that?
Yep.
Okay. That's true for any continuous function on a closed interval AB. So let's look at some examples now. We looked at this one, we found it. So here's some function. Here's my closed interval AB, right?
Yeah.
Is this function continuous on that closed interval?
Yeah.
Yeah. Here's f of B. Here's f of A. Notice that f of A can be a bigger number than f of B. It can be a smaller number than f of B. There's no restriction that way. Pick any number between f of A and f of B. Here it is. Why not? Then there must exist some number C such that f of C is equal to y naught. Now notice in this case there's multiple. There's one here, we could pick this number as our C. There's one here, we could pick this number as our C. There's one here, we could pick this number as our C. The intermediate value theorem does not say there's one and only one number. It says there's at least one number between A and B, call it C, such that f of C is equal to y naught. Go ahead.
You might want to give them the notation of there exists only one. What were you saying again?
Oh, when it's a unique.
Yeah.
So Peter's saying if we want to say one and only one, this is the notation we use. There exists with an exclamation point after it. There exists a unique or one and only one.
The E is stands for what now?
The E is there exists.
Oh, this.
Existential quantifier, same thing we talked about last night in logic, or in philosophy, I mean.
Right, I forgot. I thought mine meant every or something. Forever.
Nope, that's this one, for all, for each, for every.
Yeah.
Universal quantifier. Okay, so yeah, this is the existential one. It says there exists. Go ahead.
Why is it a closed interval, not an open one?
Why is it a closed interval and not an open interval? Well, we are very interested in closed intervals in calculus. A lot of problems, a closed interval just makes natural sense to talk about, even for real world problems that you often want to talk about. If I want to say Peter went a certain distance and he started at time equal 1 and time equal 2, we typically want to include those times. If I say, how far did Peter go in the past second, I'm not saying let's start our clock at 0 and go up to, but don't include 1 second. Say, ignoring right at 1 second, but not quite including it, but we talk about it like that. If I want to say what you did for a second, we're talking about an interval of time like that, right? If I say Peter went 10 meters, then we might say he started at 0 and he went over to 10, and this is the interval that we're talking about. And so there's just a lot of natural conversation that we have where we're interested in closed intervals. Closed intervals are very useful things to talk about.
Okay.
And so it's just something that we focus on a lot. Now, closed intervals also behave nicely. You might remember some vague notions of things like sequential compactness that we proved is true for closed intervals in topological spaces. So there's a lot of nice properties that closed intervals have that I can't explain to you in a calculus setting right now. But they just have a lot of nice properties. They behave very nicely. And so we prove a lot of things where the domain of our function is closed intervals.
Okay.
But is it necessary?
Is it necessary? For this case, notice that if our function isn't defined on a closed interval, now I can't talk about f of A and f of B necessarily.
Okay.
That makes sense.
So it just keeps things nice. Closed intervals is a general rule. So we like talking about closed intervals. They're very useful and they have nice properties. Okay, let's look at one more. Let's look at the one case that breaks the intermediate value theorem, shall we? So here's A, here's B, here is some number c, I won't call c, here's some number, and well, let's look at the constant function which starts here and ends here, right? Now this is the one function that breaks the intermediate value theorem, right?
Why would it break it?
Why would it break it? Wonderful question. What's f of a?
That.
This point right here, right? And it's also f of b.
Okay.
Pick a number between them.
Gotcha.
F of a, that works. Is there a point in this function that maps to f of a?
Yeah.
All of them.
All of them. Oh, so it always works. So there is an exception, and the theorem's always true.
What?
Yeah.
There is no exception to the rule.
Okay.
The theorem's always true, even in this case.
It's just everything's equal to the same.
Yeah, it's just a constant function. What's the point? It gives me a value between this point and this point everywhere on the interval, because it gives me that exact point. Good?
Yeah.
So there are no exceptions to the rules. A theorem's a theorem. Good? Okay. I think that concludes 2.4. 2.5, thank you. And now we'll just start going through. That's it for new material. Now I think we'll just do a bunch of example problems with the intermediate value theorem. Then we'll be done with the section, and we can move on to the next section.
You're gonna want to shift the camera.
Thank you. So intermediate value theorem, let's see where the intermediate value theorem can be useful. So this example says, show that x cubed minus x minus 1 equal to 0. See if I got that right. X cubed minus x minus 1 equal to 0. Show that this has a solution between 1 and 2. So I'm going to prove that there is some number between 1 and 2 that gives me a solution to this equation.
That makes it equal to 0.
Yeah, that makes the equation true.
1.
Does 1 make it true? Let's plug in 1. When I plug in 1, what do I get?
1.
Let's say that this is also equal to f of x is equal to that. Let's say f of x is equal to that, and now I want to know solutions to f of x equal to 0. So f of x equals that. I'm looking for solutions that make f of x equal to 0. Okay? So what does f of 1 equal?
Negative 1.
Negative 1. What does f of 2 equal?
5.
Anyone gonna argue with that?
No.
5.
That's right.
That's right. So whatever this function looks like, here's 1, here's 2. Whatever it looks like, we have no clue. Doesn't matter. The point is, at 1, the function is down here at negative 1. So the function is down here at negative 1. And the function at 2 is up here at 5.
Okay.
So whatever it does in between, we know by the intermediate value theorem that I can choose a number between negative 1 and 5, namely 0. 0 is between negative 1 and 5.
Yeah.
Is this function continuous?
Yes.
Sorry, is this function continuous? Yes.
No.
So since this function is continuous, and it's continuous from 1 to 2, then I can pick any number between f of 1 and f of 2, namely 0, that's between them. That's my why not. And I'm guaranteed that there must exist some c in here, such that f of c is equal to my number in between, namely 0.
How do you find that?
Doesn't matter. The point is, we now know that that exists.
I think you got your image messed up. Isn't that c supposed to be 0? Or do I have that wrong?
No, c is the input between 1 and 2.
Oh, c is the 0.
The input.
Yeah.
It's what gives us 0 when we plug into the function. It's the solution. we're guaranteed now that there is a solution between 1 and 2 to this equation.
So you're not trying to find a solution, just prove that there is one.
To just validate at least that there is one. No sense going looking for solutions that don't exist.
Okay.
And then sometimes it's easy to calculate the solution. Sometimes it's not so easy to calculate the solution. And instead what you can do is kind of zoom in on where the solution might be. All right, let's do another one like this. So they want us to show that square root of 2x plus 5 is equal to 4 minus x squared. So our job is to prove that there is an x that makes this true.
Okay.
You with me?
Mm-hmm.
So I'm just going to rewrite this. I'm just going to say let f of x equal the square root of 2x plus 5 minus 4 plus x squared. So basically what we get when I move this over here.
You're trying to make it equal to 0.
So now I'm looking for solutions to f of x equal to 0. If f of x is equal to 0, then this will be true. What can I do for you? You sure can.
For me?
You're born now.
Okay, so we are looking for solutions to the equation f of x equal to 0. Right? That's what we're after. So first off, look at this function. Is this function continuous?
Yeah.
Yep. Okay, so the function's continuous. So now let's pick some interval and see if we can find some interval, 2 points, one which makes this negative, one which makes it positive, and then it must be 0 somewhere in between. So let's see, what do we get when we plug in 1?
Root 7.
We get the square root of 7 minus 4 plus 1, which is equal to root 7 minus 3. You with me?
Yeah.
Is root 7 bigger or less than 3?
Or less.
Less.
How do you know?
Because square root of 9 is 3.
Because square root of 9 is 3, so square root of 7 is smaller than that.
Okay.
So this is equal to a negative number. What negative number? Who cares? The point is it's negative. With me?
So all you need to do is find any negative and any positive?
Exactly.
Oh.
Now let's plug in f of 2. What is that equal to?
9, 3, 9.
It's just equal to 3, right?
Yeah.
Yep.
Minus 4 plus 9.
Plug in 2. 2 times 2 is 4, plus 5 is 9, square root is 3, minus 4 is negative 1, plus 2 squared
Good picture of that one, it's not that quick.
is equal to 3. Okay, so, which is a positive number. So at 1 it was negative, at 2 it was positive, it must be 0 somewhere in between. So I am guaranteed that there exists C in the closed interval 1 to 2 such that f of x is equal to 0. I'm guaranteed it by the intermediate value theorem. Good?
So in solving these, all you need to do is find the negative, find the positive. and
That's it. You're just proving that it has a solution.
Okay.
You don't have to go find the actual solution.
But some of them might not, so how would you find that? By just plugging in a bunch of numbers and seeing how it comes out?
No, you'll have to come up with ways to reason that it doesn't.
Okay.
Never just keep plugging in numbers.
How do you, what does that look like?
Doesn't prove anything to plug in a million numbers.
Right.
Plug in bigger numbers and it just like keeps getting bigger than it's obvious that it's, you know.
Might give you a hunch that something's there.
All right. Not sure why they're having all that conversation. Anyways, let's look at another example. Show that f of x equal to f of x equal to x squared plus x minus 6 over x squared minus 4, where x is not equal to 2, has a continuous extension at x equal to 2. Okay, continuous extension. What's a continuous extension? Basically, if we have a function that goes along like this, has a hole, and then continues on its merry way, a continuous extension is when we just fill in the hole.
Isn't that all over the function?
No. The continuous extension is when we take a function that has a hole and fill it in. Let me give you an example. So if we take the function f of x is equal to sine of x over x. So if you were to graph sine of x over x, notice you can't plug 0 into that, right? But sine of x over x gets closer and closer to 1 as x gets closer and closer to 0. We already proved that. The limit as x approaches 0, sine of x over x is 1. So this function, if you were to plot it, it'd look roughly like this. Close to 0. With me?
Yeah.
But it has a hole right here. We can't actually plug that in. We know that the limit is 1, but it doesn't have a value right there. Good so far?
Yeah.
If I go, so this is where x is not equal to 0. If I then add to this function, and 1 where x is equal to 0, that's filling in the hole. So we just did a continuous extension of this function.
So you just put in a constant for the film.
You plug in the hole, and it makes the function continuous at that point now.
Wasn't it already continuous?
Not at this point, because it wasn't defined at that point.
Not at that.
But the
Yes.
function is continuous, right?
The function is a continuous function on its domain. The domain didn't include that point. We filled in that point. We added it to the domain. You're fine. Okay, so that's a continuous extension. So now let's look at this function. And they're saying this function has a continuous extension at x equal to 2, I believe they said. Show that this has a continuous extension at x equal to 2, and find that extension. So looking at this function, what does this function look like? Well, what do we want to do? First thing we do with these functions?
Factor.
Factor, always factor, right? So the same thing as f of x is equal to, in the numerator, what do we get?
X plus 3 times x minus 2.
2.
Good? Now, here's the general case for functions like this. When I have functions like this, and notice that when I factor them, I have the same term showing up in the top and the bottom.
Yeah.
Anytime I have something that looks like that, what that is telling me is that my function has a hole at that point too.
Yeah. Wait. Negative?
You might remember that we did the function, let's see if I can remember what it was. X squared minus 1 over x minus 1. And this was equal to x plus 1 times x minus 1 all over x minus 1. And then you can cancel out top and bottom when you needed to. When we did the limit, as x approached 1 of this thing, it was equal to the limit of this thing, which was equal to the limit as x approaches 1 of just x plus 1, right? Which was equal to 2. So if we were to graph what this function looked like, it was a function that behaved just like this, x plus 1, but had a hole at 2. So this function behaves the exact same as this function. The only difference between this function and this function is I can't plug 1 into this. Sorry, a hole at 1. That's the only difference. Notice this is equal to this, right? This spits out the exact same values that this spits out. They're equal. The only difference is I can't plug 1 into this. I can plug 1 into this.
And we want
That's
to
the only difference. So if I were to graph what this thing looks like, it looks like we have a hole, a hole at 1, so somewhere up here, with a hole right here. That's graphing this function. If I graph this function, it fills in the hole.
But they're still equivalent.
Everything that makes this true also makes this true.
Okay.
There's just one number that you can't plug into this that you can plug into this. So for every number that you can plug into this, it spits out the exact same value that this spits out. Make sense? Okay, so when they cancel out top and bottom like that, what does that mean? That means you had a hole in your function somewhere. And so the continuous extension is just filling in that hole. In this case, canceling out top and bottom fills in the hole. Right? We could have also, instead of doing that, we could have done a continuous extension of this function by saying f of x is equal to, and we'll say x squared minus 1 over x minus 1, where x is not equal to 1. And then we'll say 2, where x is equal to 1. This function is the exact same function as this function, x plus 1.
Okay.
Believe it or not, it's just a lot messier way of writing the exact same thing. We went to 1, 2, 1, 2, filled in the hole. Make sense? Okay. So now back to the example we were actually doing. Okay, show this has a continuous extension at x equal to 2. So f of x is equal to this thing, cancel out top and bottom, is equal to
X plus 3 over
x plus 3 over x plus 2. Again, where x is not equal to 2, then those two functions are identical. It's only at 2 that they may or may not differ, right?
Okay, but our domain doesn't include -2 either, does it?
Thank you.
And that's not something that we can fill in.
And that's not something that we can't fill in.
Did you fill -2 by getting rid of it?
So, this is going to show us two different types of problems with our function. When it cancels out top and bottom, then it turns out our function just had a hole at that point. When it doesn't cancel out top and bottom, then your function has a vertical asymptote at that point. So, give you a rough idea of what I now know this function looks like. Whatever this function looks like, we're going to be super, super rough. I know that it has a hole at the value 2. So what do we get when we plug in 2? We get 5 fourths.
Value 2 when it's -2.
What?
You're getting rid of the -2. Why is the whole at 2?
I cancel out top and bottom x minus 2, right? So the hole's at 2. Oh, because 2 is what broke it. 2 is what I cannot plug into this. Ignore this second term for a second. Pretend it was just this.
Okay.
X plus 3 times x minus 2 over x minus 2. The only number I can't plug into that function is 2. Because then we're dividing by 0. So 2 is what makes this whole thing 0. So there's a hole at 2, whatever this function looks like. And then the fact that there's this x plus 2 down here that we can't get rid of, it doesn't cancel out with anything up there. That means over at -2, we have a vertical asymptote for this function. That's what those ones look like. So the zeros in the denominator that you can cancel out means that you have a hole in the function. The zeros in the denominator that you can't cancel out typically mean you have a horizontal asymptote.
Vertical.
Or a vertical asymptote. Typically. We'll do more with asymptotes in the section right after this. So we'll focus on the holes for now. So on the holes for now, focusing on that. This function is the same as this function where we don't plug in 2 and -2. Right? So now the only question is, so I know that I can't plug 2 into this function, but can I do a continuous extension of this function at 2? In other words, is whatever my function doing, is it just a hole at 2 and the function is going like this? Or is the weird thing going on at 2 something different from a hole that I can't just plug in? Maybe there's an asymptote there. Maybe as my function's approaching 2, it's going like this, or it's going like this, or it's going like this. How do I know that it's really approaching the same point, but it's not quite 0? How do we check that? If it has a limit at this point, if it has a limit at 2, then the function must be approaching a value. So the question is the limit as x approaches 2 of f of x, what is that?
Just 5 over 4, right?
Just 5/4, right? You already know how to calculate that. So this function, whatever this function is, it had a hole at the value 2 5/4. And we can do a continuous extension at that point by filling in that point.
But we can at -2.
Yeah, ignore the -2 scenario for now. We'll come back to that one in a second.
Okay.
Okay, but yeah, if we had the point 2 and 5/4, that would plug that hole. So you're learning how to plug the holes if you need to plug the holes.
Okay.
Good? Okay, so that finishes this section
That's it?
for 2.5.
5.
We haven't started 2.6 yet.
Oh.
2.6 is limits involving infinities and asymptotes. So here's actually what we're going to do. We're going to slow down a bit in the class for a week and let you guys re-get some footing. So we'll spend the rest of the class going over questions, answering any of your questions. Tomorrow, I guess I can end the lecture. This is lecture stuff.